Okay, let's go ahead and get started here. First of all, hopefully a short story. Um, we've been able to connect with Quill's family. Um, Mom posted pictures there of him on the plane ride home. Had enough. No, I don't think they had to buy a seat for him. He basically just, laid down and slept on the floor. Evidently, he did okay with the flight. She's posted some pictures, since they got home. The family has a pet dog, so there was a video of that dog and Quill running around in their backyard. They had to go through basically 2 weeks of training at Four Paws before they were allowed to take the dog. And I guess at some point in time, they were told the dog will respond to this whole long list of commands. And again, Quill is been evidently doing such a good job alerting people. He barks basically if the boy starts having a seizure, and he's been so good at doing that. Mom is very, very happy. But they were also told that, okay, if you give the dog a command, he'll obey it. It's not a problem. If the dog isn't actively, looking out for your child, and you don't give them something to do, they get bored, and then basically they act like a 10-year-old boy. Well, the other day, they let Quill out in their backyard to go potty, and then they kind of forgot about him for a little bit, and then when they went to call him back, yeah, did I mention 10-year-old boy? Yeah, he found the mud. And yes, that is actual mud on his tongue that's hanging out there. Mom said something about I laughed longer and harder than I should have when I saw that, and then Dad had to give him a bath, which good for you, buddy. I've been doing it for a year and a half. Again, he weighs like 85 pounds, and I swear 20 of that has to be fur. So I thought you guys might be amused at the little picture there. Okay, let's go to what are we reviewing here? Section 6. I have a quiz ready for you to take over 4, 5, and 6. So let's talk about all of this lovely tournament stuff and Hamiltonian paths. And anybody have any questions?
Can we go over number 7?
7, sure. Oh, yeah, the challenging. Find all of them. How do you know when you found them all? All right, so one of the key things is figuring out where you can, or I guess more to the point, pun intended, where you can't start. For figure A, tournament A, not sure how to call it here, we're looking for basically the rays, these directed paths, where, okay, D isn't going to work because all of them end there. Evidently, Team D was horrible in the tournament and lost absolutely everything that they played because all of the arrows end there. For A, point A, team A, there's only one. So if I started at point A, I would have to go to D, and that's pretty much a dead end. Okay. So we're looking then for a point that has basically the most starting points, potentially. So in this case, it's B. Evidently, because again, the way that the directions, the paths are drawn here, B was 3-0 in this tournament. So we'd start with B. Then, again, they beat Team A, they beat Team C, they beat Team D. If I go B to D, that's a dead end again. So I know D has to be the last one here. If I go from B to A lost to C, that's not going to work. So the only real Hamilton path here is B, C, A, D. Does that make sense?
I think that's 5.
Uh-oh. I went through all of that, and now you tell me, hey, you're doing the wrong stuff.
Did I do the wrong thing? I was very scared for a second.
Oh, I'm sorry. I made you question. Nope, absolutely right. I just didn't scroll up enough for today. Here we go. Yay, the 4-color problem. I'm sorry. Again, working on your quiz, all of this seems rather fresh in my mind. Here, how about it's 7, right? Now that I have the right section, let me get the right problem number. I'm sorry. A cycle. And again, we've talked about Euler cycles and Hamiltonian cycles. A cycle is a path that begins and ends at the same spot, does not use any edge or more than once. If a cycle has an even number of vertices, what's its chromatic number? Okay, so again, we talked about taking a map and turning it into a graph, and then looking at endpoints and representations there. Really? I took that out. We'll get there eventually. So for an even number of vertices, say 4, and there's supposed to be a cycle, so that means, do I need to label these? Something like that. Okay, so I could go A, B, D, C, back to A and complete that cycle. And with the even number of vertices, now again, I don't know, maybe I shouldn't have. Don't want to confuse people here. Maybe it was one of those lovely curved paths, so we don't have any confusion about how many points of intersection here. Every single one of those points is has 2 paths there. So in this case, it looks like the chromatic number is just going to be 2 because that's the highest value there. Let's try 6. 2, 3, 4, 5, 6. And again, if there's a cycle that begins and ends with the same vertex, now, again, I could come up with all kinds of different variations here on, their definition of a cycle here begins and ends at the same vertex, does not use any edge or vertex more than once. If I do something simple like this, again, every single point here has 2 paths to it, so the chromatic number there would be 2. Now, it would be interesting to see the process there of taking a graph with a particular chromatic number and see what you guys would do turning it back into a map. For something like this, where there's an even number of vertex points and there is a cycle, I don't know, seems like that map would have to be rather simplistic. For part B, with the chromatic number of a cycle with an odd number of vertices, well, I'm not even going to do 3. That seems so simple that it's not worth our time. See what I did there? I almost, but that was such a terrible pun that I decided not to. And again, there's supposed to be a cycle. So if I've got something with, say, 5 vertex points, again, I could go through the rather simple walk around the perimeter here. Can I do something more complicated? But, I mean, even doing that, I wonder if there's something that, again, it doesn't use a vertex more than once. So say we have a complete graph here. And then I'm saying we go in that way to finish it up. The chromatic number here, each of those is 4. So, again, I'm wondering if I go back to my earlier ones and make them more complicated, but stick to that path. Thank you. Can I do that? Again, if none of those points of intersection on the inside are actual points on the graph, I've changed the chromatic number here because, let's see, this is 3 and that's 3. This is 4, that's 3, that's 4, that's 3. Okay. Now, seems to me they talked about, where did it go? Does that Hamiltonian formula apply here? Okay. Gotta scroll through the whole thing to find it. Well, again, I'm sorry. Again, that's for a connected graph. And my examples so far don't necessarily, well, the one with 5 is connected. The one with 6 isn't. Part C, draw a cycle with 6 vertices. Use your algorithm to color it. Ooh, does your algorithm give the correct chromatic number? Right, hold on. Yeah, that's not gonna.
My handwriting is so bad.
I'm sorry, say that again.
My handwriting is so bad.
Oh. That's okay. I mean, we're coloring here. See, I think it's more complicated than just okay. We have a graph that has a cycle. Okay. Am I missing something in our definition here? It says doesn't use any edge or vertex more than once. So that's a cycle. But now I've changed the chromatic number here. That has 3 paths, 2, 3, and 2. Maybe we should look at, again, that process that I said a moment ago. If we turn this into a map, what's it look like? Oh, let's pretend we're out west and we can just do rectangles and squares. So for point A, it's connected to all of the others. Does that work? So again, A, B, C, D. So if this is A, it's connected to B, C, and D. B is only connected to A and C. D is only connected to A and C. C is connected to all 3 of them. So in this case, I would say we need 3 colors. Okay, we could do A in one color. Again, it's adjacent to C, so we would definitely need a second color. And then they're adjacent here, so B, we would need a third color. But B and D could be the same. Now again, the theory is 4 is going to be the maximum. All right. So I think what they're trying to get at here, no, yes, I'm sorry, let me back up here. If the graph has a cycle, using an even number of vertices, is that chromatic number going to be equal to 4, or is it going to be something less than 4? That's how I'm really interpreting this now, okay? So if we have an even number, we could get away with just doing 3, okay? Now, if I do that very, very connected graph there with the, I don't know, let's just do part C then. Draw a cycle with 6 vertices. Use your algorithm to color it. Does your what algorithm are they talking about? Just that I've got to take
I think it's part of like part 3, I think, or question 3.
Oh, okay. That's what I was forgetting. It seemed like it was referring back to something there. So I guess if we go back to number 3, it's possible to begin looking at the coloring process several different ways. So basically, you got to go through and figure out the degree of every vertex, list them in order from greatest to least. Pick the one that has the highest degree, color that in, and then you've got to find those that aren't adjacent to it. Then you can give them that color. Okay, does that make sense? So again, with the one that I've drawn here that has 6, for my part C, I've got 1, 2, this is 4, 3, 4, 3, 3, and 3. So I would have to start with one of the 4s and give that a particular color. And then the ones that aren't adjacent to it, well, again, the way I've set it up here, if I'm going to start with this one and color that in, the way my graph is drawn, it's only adjacent to 4 others. There's 1 that I've missed. So again, if I do this region here in purple, then I could do this one in purple because there's no connection between them. Does that make sense? Okay. And then I think, again, using that algorithm, why didn't they say that? Use your algorithm that you created in problem number 3 to color it in. Okay. Does that help any, Bernadette? Okay.
Oh, then
All right.
also
Oh.
2B.
Is that some kind of a Hamlet joke? Draw a graph that has 4 vertices and a chromatic number of 1.
Wait, hold on. I meant 2A, sorry.
2A. Draw a graph that has 4 vertices and a chromatic number of 3. Well, okay, let me just take a picture. Come on. Why are you blinking at me? Stop doing that. There we go. So start with 4 vertices, a chromatic number of 3. So again, to me, the implication is this is connected to all of them. Or is it? So if I turn that into a map, what would I need there? So these two are connected to one another. And this one over here is only connected to that. I'm not sure if I can do that. Does that work? Because if this one, again, has a degree of 3, that means it's connected to 3 different regions. This one only borders 2, this one only borders 2, this one only borders 1. So again, if I started with this one here as purple, then I would have to say this one's green and this one's blue, because again, they all border each other, so I can't overlap that. But for one, I could go back to green because they don't share a border. Okay. So with the chromatic number of 3, you're going to have one region. I don't know. We could explore this, for the next hour and a half, and come up with how many of them border 3 regions. But I think one of the keys there is that that has to be the highest degree. You can't have a point in there where, although it's got 4 points, something's connected to, well, yeah, that there are 4 paths. How would you do that with 4 paths, though? To me, having the chromatic number of only 3 means you have to simplify that down so that you could repeat Again, remember our maximum is 4. So if we're going to knock that chromatic number down to 3, of these 4 different places here, we need to be able to repeat one color, which means, okay, there are 2 different regions that aren't connected somehow. Okay. So again, I've accomplished that here with the 1. If I connected it with the 2, I don't know. I guess that would work, but just making sure it's not a complete graph so everything doesn't border everybody else. Does that work? Draw a graph that has 4 vertices and a chromatic number of 1. How'd you guys do with that one? How could we position the areas on the map?
I just put it like that. I just like left them unconnected.
Oh, I don't know how to do that with.
I just kind of left them unconnected, and I think that would work because the regions would be separated, therefore not adjacent.
What, you drew like 4 islands?
I mean, yeah. That's the only way that makes sense, yeah.
If they're not connected, then they don't share a border, right?
It does not say that they have to be connected. It just says 4 vertices.
Yeah, that's like the world's most boring map. Here, look, we've got an entire archipelago of islands. Oops, hold on. Got to undo that. Yeah, I don't even think what I've drawn there works. Because if, again, A and C are connected to one another somehow on my map, if they are adjacent to one another, I would have to use 2 different colors. Okay? So, yeah, as far as the graph is concerned, I don't think you could have anything connected, because I mean, even if I did something simple like, well, here. So C is, stop it. So C is over here by itself, and D is over here, and they don't. But if the border between A and B is connected, then I would need a second color to distinguish those 2. So I'm thinking we need something that has 4 vertices and no paths, no connections between them. How's that sound? Kind of wild, huh? All right, we're down to only 10 minutes here, and I want you to, I promise the problems I put on the quiz aren't going to be tricky. Let's see, I need to stop doing that. And then Really? Why is that a thing? Okay, my confuser says it's done. We'll see how long it takes for it to pop up for you guys. Come on, here we go. Or does it just take a while for my computer to sync with yours? Okay, so as soon as that pops up, you can start filling that stuff out. If you want to then leave the meeting, that's fine, so you can concentrate on work. I hope you all have a safe and happy Thanksgiving, and oh my goodness, our next meeting is scheduled for December the 1st. So, yeah, I'll see you in a week. Be safe. All right, now get to work. I'll stop distracting you. Bye. Listen to you.